Hello everyone, hope you all doing well. My name is Panda, and in this video we will be discussing another design pattern from chapter 2 of the book Machine Learning Design Patterns. Today's pattern is called embeddings, and its purpose is to convert a large number of features, such as those coming from one-hot encoding of many categories, into a smaller compressed representation that captures the relationships between the features. As was last time, and as we agreed in general, we will first look at the problem and try to understand its aspects. Then we will explore how this design pattern solves the problem, followed by discussing its advantages, disadvantages, and when to use it and when not to. Let's start with the first thing, the problem, and the challenges at the beginning. As we know, the model learns by taking data as input to identify the relationship between inputs and outputs. We have also seen that data may sometimes come in forms unsuitable for direct input into the model. In the last video, we dealt with a feature that was text, the name of the airport, and we needed to convert it into a numerical format to handle it properly. Similarly, other data types like categorical features, images, audio, and many others can't be directly fed into a model. These also need to be converted into numerical formats to work with them. If we go back to categorical features, we mentioned that we can use one-hot encoding. For example, if there is a pregnant woman about to give birth, there is a possibility that the baby could be a single baby, twins, triplets, quadruplets, or quintuplets. This results in 6 categories, and applying one-hot encoding would require 6 dimensions to represent them all. While 6 dimensions might not seem too large, the problem arises when we have many categories. For instance, if we are dealing with data from YouTube, we would have many users and videos. The goal might be to recommend a list of videos based on users' history. In this case, we might have millions of user IDs and millions of videos IDs. Using one-hot encoding here would bring up the issue of high cardinality, which we discussed in the previous pattern. This would result in sparse features, and as we mentioned before, most models can't handle sparse data effectively. So, is there a way to reduce the cardinality or dimensions while still differentiating between the categories? Let's look at this representation. As you can see, each category is represented only by 2 dimensions. If you focus a bit, you will notice that the numbers in the first dimension are for the single and 0 for the multiples, while in the second dimension, the values increase as we go downwards or as the number of babies increase. These numbers don't mean anything by themselves. They are just to illustrate the idea that you can represent your features in a compact and meaningful way, using fewer dimensions, like 2 dimensions here instead of 6. Additionally, this representation is more logical. Instead of looking at just one number out of 6, which made it sparse, now we look at 2 numbers together to understand the category. This is exactly the problem that today's design pattern, embeddings, aims to solve. The same cardinality issue exists in images, since an image consists of thousands of pixels, and not all of them are independent of each other. There are relationships that link the pixels, such as neighboring pixels have similar values. If we look at text, we'll find that certain words are also related to each other, while others are not. For example, the word walk is closer in meaning to run than it is to book. If you are paying attention, we have now gained a new perspective on the concept of categories. It's not just about reducing the number of features we need, nor to only be able to differentiate between them like in one-hot encoding. It's also about introducing meaningful relationships between them. Looking at one-hot encoding, we see that it doesn't establish any relationships. However, in the previous example, when we used 2 features instead, there was indeed a relationship between them. Let's see how embeddings solve this problem. The embedding design pattern takes high cardinality features and transforms them into a low dimensional representation that retains most of the essential information about the categories and the relationships. This is done by passing the feature through an embedding layer, like the one found in the transformers for text. The embedding layer contains weights that are learned during training, with every backpropagation step. These weights are trained alongside the model to learn the best representation for each category based on the training data. If this part is confusing, rewatch it because it's very important going forward. For example, let's consider polarity as a categorical feature. Instead of applying one-hot encoding and generating 6 features to represent each category, we replace it with a learnable embedding layer. Now, instead of creating 6 features, we only create 2 features. Here's an additional note from the book. If you're using an embedding layer, you don't need to perform clustering or PCA beforehand. These methods also aim to capture relationships between data points in a lower dimensional space. And the embedding layer already does that. Let's look at the representation we get after applying the embedding layer. The relationship might not be as clear as in the simplified example we showed earlier. But if we examine the first feature, we notice it decreases as we move downwards. However, the second feature is less intuitive. But if we plot this on a graph, we can derive meaningful insights. As you can see, single are positioned far to the right, and as the number of babies increase, it shifts further to the left. This makes perfect sense if we think about it. Also, quadruplets and quintuplets are close to each other, as are triplets and multiples. Not only did we reduce the dimensions of the categories, but also we captured the relationships in a logical way. If we calculate the cosine similarity between these categories to measure how similar they are and compare the results for both one-hot encoding and embeddings, we'll notice a stark difference. With one-hot encoding, there are no relationships between features. Each one is entirely independent, and all values are 0 except for the one corresponding to the feature itself. However, with the embeddings, every feature has a logical relationship with the others. For instance, 5 is closest to 4, which is closest to 3, and so on. The farther you go, the less similar they are. This is exactly what we want to achieve with text. When training a model on a vocabulary, the vocabulary size is often too large for one-hot encoding, and the relationships between words become crucial. That's why architectures like Transformer include an embedding layer to handle vocabularies of say 50k words or tokens. Each token is represented by a vector of let's say 1024 dimensions. Instead of having a sparse vector with 50k entries, all zeros except for 1, now this 1024 dimensional vector is rich with information about the token and its relationships with other tokens. We can also do a similar thing for images. We can use convolution neural networks pre-trained on datasets like ImageNet, for example ResNet or Inception. We discard the softmax layer at the end. Now the final layer of the CNN can serve as a feature vector for the image. Instead of representing the image as a 1000 by 1000 grid, we can create an embedding which is a final vector of say 2048 dimensions. This vector contains all the critical information about the image in a much smaller representation. A straightforward application of this concept is image captioning. We can take a CNN model without a softmax layer to extract a feature vector. This vector is then passed to a decoder as input, like an RCNN, which generates text as the output, providing captions for the image. Now let's return to the YouTube recommendation example, with users and videos. If we replace one-hot encoding for users and videos with an embedding layer, each user now has a vector representation, as do the videos. We can measure how similar two users or videos are using metrics like cosine similarity or dot product. With the history of videos a user has watched, we can determine which other videos are similar to them and make personalized recommendation. Here's what the final features look like when passed into the model. The customer is represented by an embedding of a certain dimension, and the videos they have watched are also embedded in another dimension. We will discuss in a few slides how to decide the size of these dimensions. So far, we have defined the problem and explained how the embedding layer can solve it. Now we will move on to the trade-offs. Much of what follows will feel like notes to keep in mind when using the embedding design pattern. The first note, which we have already mentioned, is an important trade-off related to the size of the embedding layer. For instance, in the first example, there were 6 dimensions, which we reduced to 2. For the image example, it originally had 1,000,000 pixels, and we reduced it to 2048 dimensions. But how do we decide the size? If the embedding layer is too small, it won't capture all the necessary information, and the embeddings won't represent the categories effectively. If it's too large, we're back to the same problem as one-hot encoding, where features are unrelated to each other. The size determines how much information we are willing to lose, while compressing the features into a smaller dimension. This is similar to the trade-off between bias and variance. The book suggests 2 rules of thumbs when choosing the size. use the fourth root of the number of categories, or use the square root of the number of categories multiplied by 1.6, assuming that categories are more than 600. For example, if a feature has 625 categories, the first method suggests a size of 5. The second method suggests a size of 40. Treat the size as a hyperparameter for your model, and test it between values 5 and 40 in this case, to find the best one. Another important topic is autoencoders. Training an embedding layer can be challenging because it requires large amount of labeled data. For example, when we used a pre-trained CNN and removed the final layer, those models were trained on ImageNet, which contains 14 million labeled images. In most cases, we don't have access to such a large amount of labeled data. An alternative approach is to use autoencoders. In an autoencoder, we take our unlabeled data, Wikipedia for text or Pinterest for images, and design an embedding layer that compresses the data into a lower dimensional representation. A decoder then takes this representation and reconstructs the original input. The idea is that the input matches the output, allowing us to leverage the unlabeled data to train the model. The model learns to generate a rich representation in the lower dimension, while retraining enough information to recreate the original input. When this happens, the representation contains all the critical information about the input. Once trained, we can take just the embedding model and use it for other tasks. For example, if the task is image classification with limited labeled data, but a lot of unlabeled data, the embedding model has already learned a significant portion of the task using the unlabeled data. You now only need to add a classification layer to learn from the small amount of labeled data. Since the original task was image classification and we designed another task which is to train the embedding layer to help us in the main task, this is called an auxiliary learning task. But does this work for text? The answer is yes. Models like Word2Vec and BERT are good examples for that. Both take text as input and output a vector representation of the text, which can be used for other tasks like text classification. I won't go into the details of Word2Vec or BERT here, but the goal and methodology are similar. And that wraps today's design pattern. We have solved an important problem that anyone in our field is likely to encounter. And we also saw how this pattern helps address it, and what to watch out for when using it. And that's basically it for today's video. I hope you found it useful, and if you have any questions, leave them in the comments, and if you have any feedback, please share it as well. See you in the next video with a new design pattern, inshallah. Bye bye.